Good morning and welcome, honor students, and happy Friday. It is Friday, so I wanted to do a virtual lesson today and introduce Chapter 14 to you. You might be wondering, why would I want to be starting Chapter 14 when we're going to be testing on Monday on Chapter 13? Well, the reason behind that is this particular section will actually help you to further understand the kinetic theory as it pertains to gases, which is what we covered in 13.1, if you think back onto that. So this will actually be of help to you. So it'll help you review that particular section. So today we're going to begin 14.1, the properties of gases. So we're going to look at it just a little closer. So please remember, on Monday is your virtual test. It'll be on Moodle. So I placed a link on Moodle for you to look at, and then I will open that test for you on Monday, and you have to get it done on Monday, and it has to be a 45-minute session at the most. So please do remember it is timed. So once you start it, you can't walk away from it. You have to finish it up. So 14.1. So we start off with a case file, as we typically always do. Here it is talking about a soccer ball. And when you buy a soccer ball, or you could say a basketball or a football, whichever sport you might be into, you might notice that it has a pressure requirement. On a soccer ball, it typically says 0.6 atmospheres and no higher than 1.1 atmospheres. I think about, why is that? Well, if you go between 0.6 and 1.1, the ball is hard, sufficiently hard enough to have a little bounce to it to be able to kick it and go further. We'll talk about why would you not want to place it, say, at 1.5 or 1.6 atmospheres. We'll talk about that. Compressibility. Now, that's a key concept and a vocabulary term as well that you'll get down. Why are gases easy to compress than solids or liquid? Well, we learned in chapter 13 a little bit about the particles and how they are. So solids are rigid and tightly packed, vibrating in a fixed position. Liquids, we talked about them flowing past each other. There is attraction, so they're fairly close, but they're not rigid. They can flow. And then there's gas. Gas, there's no particle attraction. So they flow, but they move past each other, rapid, random, and constant, if you remember those terms that we talked about earlier this week. So let's talk a little bit, why are they easy to compress? So let's get this term, compressibility. So please make sure you get this term right here into your new set of notes. Compressibility is a measure of how much the volume of matter decreases under pressure. So compressibility, how compressible is something? Well, if you think about a solid, if you try to compress it and push on it, it's not going to go very far. It is not compressible. You think about a liquid, and we talked about this earlier in the week. That is why liquids, particularly oil, which is liquid, is used in hydraulics, and that is what backhoes and loaders and a lot of heavy machinery use to move the parts, is hydraulics, which is oil, because a liquid is not easy to compress. Think about a gas. Let's think about this for a second. If you had a syringe in your hand and you pushed on the end, you trapped the one side and you pushed on it, you would be able to almost all the way down press that syringe, probably 3/4 of the way. Can't go all the way because there is particles in there and it will not allow you to go beyond a certain point. There's a lot of space between those gas particles, and you can compress them down. So here's what it's talking about right there. Gases are easily compressed and squeezed into a smaller volume. And that's very beneficial. We talk about airbags, which you see the picture right here. They absorb a lot of energy, and that's why they're so useful in cars and accidents, because the energy is absorbed, so it compresses the gas further and saves a lot of personal injury to a person by that. And so there's so much space, so gas particles can be compressed. So key concept. Gases are easily compressed because the space between the gas particles, the volume of the particles in a gas is small compared to the overall volume of a gas. Remember, small hard spheres with insignificant volume. That was from earlier this week. So that's really important to understand. You talk about the gas molecules are very small and there's a lot of space in between them, so you can push them together. The distance between the particles in a gas is much greater than the distance between liquids and solids. And under pressure, the particles are forced together, and you are able to do that. So here is a little bit of an idea. You have 8 nitrogen and you have 2 oxygen. You see the oxygen here in red and there, and then you have the 8 blue, which is the nitrogen. They're in a large container. They're bouncing back and forth. That's what gases do. They move rapid, random, and constant, striking perfectly elastic collisions. All energy is retained. So what happens if you make a smaller container? The gas still fits. You can see right here, much smaller, at least half the size, but the gas still fits in there. But it's under more pressure now because there's not as much area for them to move, so they're hitting and moving faster, which is causing more strikes on the sides, which is increasing the pressure. We'll talk a little bit about that. So, checkpoint. Explain why air is easily compressed, but wood is not. It's pretty straightforward. I won't spend a lot of time on that. Wood is solid, it is rigid, the particles are moving, vibrating in a fixed position. All of them are vibrating in a fixed position. Please make sure you notate that. But when you talk about air or any type of gas, they're moving rapid and constant and random, but in a lot of space, taking up a lot of space because there's no attraction. All right, there are 4 variables that we are going to be using inside of chapter 14. We're going to talk about moles, which is N. We're going to talk about volume, temperature, and pressure. So we're going to be using V, T, pressure, and N. And those all are correlated, and those variables are very important when it comes to a gas and calculating gas pressure. So the amount of gas, volume, and temperature are factors that affect gas. And we're going to learn that in this section. There's formulas that we're going to go through. There's worksheets I'll be assigning, and you'll become very proficient with it. We'll work through a lot of examples. So the amount of gas. You can use kinetic theory to predict and explain how gas will respond to changes. So if you inflate a raft, the pressure inside the raft will increase. You're adding more gas. Same concept with a balloon. If you take a balloon, you blow it up halfway. You'll see the size that it gets. Now you can force more air into there. Now you have more moles going into there. And then it's going to get bigger until a point that it can't hold it anymore. Collisions of the gas particle with the insides of the walls of the raft exert a pressure. So here you have inside, and these molecules are striking. And by them striking, they're exerting a force outward. And that is why you can see it inflating. Increasing the number of particles increases the number of collision, and that's increasing the pressure. So the more you add into here, the more collisions are going to strike. It would make sense that the pressure is going to go up. And here's what they're showing. So here you have a container and you have 100 kilopascals. That's your pressure. And you could count it here, 2, 4, 6, 8. Let's say you have 8 molecules in there. Look at what happens here. You doubled the molecules. So you went from N to 2N. Doubled it. Look what happened to the pressure. It doubled. Well, what happens if you put a whole bunch more? It's going to come to a point that it's going to rupture. So that is what happens when you add more moles. You increase the pressure, and the pressure is going to try and increase the volume. And if it's a rigid container, it can't, and it'll burst. Now, this is a concept that is used in aerosol cans. If you think about it, at the top of this aerosol can, when they make this, they have some liquid in here. It could be paint, could be hairspray, could be many different things. They force a gas into the top there. You, my little red arrow right here again, right there. They force gas in there before they sell it. Then they put the lid on it, and then you buy it. What's happening is you have a very high pressure inside this canister. Very high pressure. Very high pressure. When you release that valve at the top and push down, what you are doing is creating an avenue to release the pressure. So now it is going to force downward, and what's going to happen is whatever substance you have here is going to go up and blow out. And that's the concept of all these spray containers work. Not the spray that you have to pump, but the ones that you just push down and it blows out. That is gas pressure. So volume. You can raise the pressure exerted by a container by reducing the volume. So if you have a container this size and somehow or another you have a plunger in here, say you have 2 atmospheres here of pressure, and now you have that same size container right here, but look at what you did. You pushed down halfway with that plunger. Now you have half the space. So you have doubled the pressure. So that is a key concept. The more the gas is compressed, the more pressure it's going to exert. And you can think about that in terms of a balloon. If you blow a balloon up and then you try to push that balloon down, it is going to apply more pressure. You are reducing the volume, and that's increasing the pressure. So on the opposite token of that, if you have a container and it has this plunger in it, and this has high pressure, so the pressure is very high right here. If you have that same container and you release some of the pressure, now the pressure is going to fall because you have now increased the volume. So now there's more space for those gas molecules and particles to go. So if the volume is doubled, the particles can expand to the volume that's twice the original volume. With the same number of particles, twice the volume, the pressure is reduced half. So if we did this and we say this is half, and say we had 2 atmospheres here and we raised it half, doubled the volume, now we have 1 atmosphere here. So there is a direct correlation when we talk about that. So pistons, and we talked about this, was a little example I drew. If we have this piston and we have 100 kilopascals and we take it from 1 liter to half a liter, so we halved the volume, we doubled the pressure, and you can see that right there. Temperature, very important when it comes to temperature. And remember, we learned what temperature is. It's a measurement of the average kinetic energy, and that's a vocab word that you could be tested on Monday. So you can use kinetic theory to explain what happens as a gas is heated. The temperature increases and the average kinetic energy of the particles increase as well. So faster moving particles strike the wall with more energy. They're moving faster. So you have increased the motion, the kinetic energy, by raising the temperature. So it's absorbing that energy, making it move faster. The faster it strikes, the harder it strikes the sides of the container, the more pressure. And here is increasing the temperature causes an increase in the pressure. So here you are at 300 Kelvin and 100 kilopascals. You doubled your temperature, you doubled the pressure. And then you're going to get to a point here that is going to actually explode. The container can explode, and that's really important if there's too great an increase in the gas pressure. So that's why if you look at any aerosol container, paint, hairspray, anything that's trapped in a bottle that's under pressure, do not expose to heat. Do not leave in a trapped car, a closed car, any of those things. Why? Because if you increase the temperature, the pressure is going to increase and it can blow the container up, just as what's represented right here. We're going to do a lot of solving in chapter 14 with formulas, and we're going to calculate pressure, volume, temperature, moles, all those things. So checkpoint question. How does the pressure of a contained gas change when the volume is increased? Think about that. Is it A, the pressure increases, B, the pressure decreases, C, the pressure does not change? So the volume of the gas is increased. So if you have an increase in the volume, your pressure is going to decrease. So you're not going to have the particle striking the walls of the container as great a force because now there's more space for them to move around. So real important concept. So let's think about that ball for a second. So we have this soccer ball here. And say we have 1.2 atmospheres. That material that ball's made out of, any material has a maximum pressure that it can withstand. So somebody comes up and kicks that ball real hard. At 1.2 atmosphere, it would be able to absorb that kick and the ball will go. But let's say that you overinflated this ball and you put 2.0 atm. And somebody comes up and kicks this ball. So you have a force striking. Look at what's going to happen as that force strikes. It's going to cause a dent in that ball where the pressure is being applied in. That can make the pressure, because you now decrease the volume, the pressure could shoot up to something like 3 to 4 atmospheres, and therefore that ball could explode. So properly inflated ball will travel further because it has more bounce to it. What might happen to an overinflated soccer ball if you kick it too hard? Well, I just drew. If the pressure is too high, the ball can burst because you reduced the volume and now the pressure went up. And that's it, ladies and gentlemen, for 14.1. You may have noticed I used a lot of terms that we learned in chapter 13. So this is basically a review of chapter 13.1. So I hope you did take some notes. This is a new section, but it is very helpful for the section that we just completed. So key concept, gases are easily compressed because there's so much space between those particles. We know that the pressure, the volume, the temperature, the moles all have a relationship when we talk about gas. And we're going to learn to use formulas to help us capture and calculate any of those missing variables as we go through this particular section. We had one key term, compressibility, the measure of how much the volume of matter decreases under pressure. So that is very important when it comes to gas. Lots of space between the particles so they can be compressed. And that is the end of 14.1. I trust you have a good day. Thank you for watching. Go in peace.